Friends, this is a presentation on analysis of variance, and I want to share some slides on analysis of variance, which in short is called ANOVA. My focus will be on clarifying certain theoretical issues and showing application of ANOVA with an example. So I'm sharing my PPT with you. Friends, this ANOVA or analysis of variance is part of causal analysis when the dependent variable is a numeric variable and the independent variable is qualitative. There may be two or more independent variables also, and some of them can be qualitative. Then we will go for an advanced version of ANOVA. Right now we are considering only two variables, one dependent, one independent. Dependent is certainly numeric, but independent variable can be qualitative also. And there are three or more groups of independent variable which can be which need to be compared. If you have only two groups, you know that you can use Z test or T test for comparison of means. But when you have three or more groups, then you require application of analysis of variance or F test. And no doubt, pairwise T test is more powerful than simple T test. And this pairwise T test is part of ANOVA. So you can even use T test along with ANOVA. And this T test, this is called pairwise T test with ANOVA will be a more powerful test. Powerful means that the probability of rejection of a false hypothesis is higher. 1 minus type 2 error or 1 minus beta is higher. This ANOVA is based on F ratio, and F follows a probability distribution which is called F distribution and which looks like this. If you are not a student of mathematics, you can ignore these things, but you should know that this F we will be calculating an ANOVA follows a theoretical distribution which goes from 0 to infinity, and the figure looks like this. The minimum point on the graph is 0 and the maximum can be infinity. For different degrees of freedom, this F distribution takes different shapes. Actually, F is a family of distribution. The formula which I showed you in the earlier slide refers to a family of distribution. To arrive at a specific distribution which you must use in your practical application, you need to specify the degrees of freedom. For example, when you can apply ANOVA, 30 students are selected to examine the impact of 3 different teaching methods, and 10 are randomly allotted to each other. Different methods are used in different groups, different teaching methods, I mean. At the end of the semester, the following results are obtained, and these are marks out of 100. Can you derive any inference on the basis of differences in means of the data? These are different teaching methods. Method 1, method 2, method 3, and each of these 3 methods is tried on 10 students, and at the end, out of 100, they are achieving this. Now you see that as such, the method 2 leads to highest score, 64.6. The mean value of these 10 on whom teaching method 2 is used is 64.6, while the mean of teaching method 1 is 59.1 and teaching method 3 it is 49.9 minimum. But just by looking at means, we may not be able to say whether the differences are significant or not. I am using the term significant in terms of whether the differences can be attributed to sampling fluctuation. The whole statistics is about testing whether the differences can be attributed to sampling fluctuations. Imagine that if these data had come from a census, then we would definitely say that teaching method 2 is better, and we need not apply any F distribution or anything. But most of the time our data come from experiments or samples, and therefore application of ANOVA or such tests becomes necessary. Now friends, there are difficulties in comparing means. On the basis of means, teaching method 2 seems to be the best, and teaching method 3 the worst. The problem with sample studies is that there are a lot of variations within the groups also. So you find that in group 2, which is the best, there are some students who have scored as low as 50 or 56, while in group 3, which had the minimum average, there are some who have, there is one student who has scored 100 out of 100. So there are all kinds of variations. There are variations between the groups, and there are also variations within the groups. And therefore, some comparison of to what extent variations between groups are higher than variations within groups is required. Not all students in group 2 have done equally well. There are many students in group 1 and 3 which are better than many students of group 2. If another researcher conducts the same study, shall we get the similar results? If there are variations within the groups, that shows that we cannot definitely say on the basis of means of the groups that one group is superior to another. A lot of variations in the data are because of variations within, or sampling fluctuations, or error, or due to factors which are not explicitly or directly considered in the experiment. Imagine that you had data like this. In these data, this is a hypothetical example just to clarify my point that means are different. Group 2 has the best mean. Group 1 has the middle mean, and group 3 has the worst mean. And all the individuals, all the subjects, all the students which are part of these groups have the same mean. Now, in such a situation, fluctuations within the groups do not exist. You can say fluctuations within groups are zero. And therefore, whatever fluctuations exist, they are between the groups. And certainly you can say that there is a significant difference between the groups. There may be another situation in which all the group means are same, 50, 50, 50, but there are a lot of variations within. Now, in this case, certainly you can say that teaching methods make no difference. There are differences more due to random fluctuations or due to factors which are unknown, which have not been directly taken into consideration. The problem arises because your results are mixed. They contain both types of fluctuations between and within. So there are two types of differences within each group, between each group. They can be measured through variability. The statistical tool for measuring differences is the sum of squares. And sum of square divided by degrees of freedom becomes your estimate of variance. ANOVA is based on comparison between estimates of variance based on variations between groups and within groups. Please, I'm repeating because this is a very important point, that ANOVA is based on comparison between estimates of variance based on variations between groups and within groups. Actually, you can have three different estimates of variance in case of this simple ANOVA. One based on total fluctuations, another based on between groups, and the third one based on within. You have three different estimates of variances. Now, the ratio of variances follows a F distribution. So you can, by using F distribution, compare estimate of variance based on between groups with that within groups. And if the differences are pronounced, you can say that there are significant differences between groups. In general, your data would be like this. And the model, please note that there is a linear additive model that we are testing in analysis of variance. That model looks like this. Xij means here J refers to group and I to observations. So Xij is ith observation in jth group. Now that ith observation of jth group depends on overall mean, mu. It also depends on the effect of jth group, alpha j, if there is an effect of that, plus Eij. Eij is a random term, and we assume that Eij follows a normal distribution with mean 0 and a fixed variance sigma square E. And this property of having a fixed variance is called homoscedasticity. If there is heteroscedasticity, or if variance of the error term varies according to values of the observation, then we will have to make some correction in the application of ANOVA. The null hypothesis that we are testing in this model is that alpha 1 equal to alpha 2 equal to alpha 3, which means the true means of the three groups are same. And the alternative hypothesis in this case is that at least two of the groups differ. It's very important to understand the alternative hypothesis in case of ANOVA. Imagine that you have 10 groups. Then the null hypothesis would be that effects of all the 10 groups are same. And the alternative hypothesis will be that at least two of the groups differ. Actually, it is not possible that one group only differs from the overall. At least two groups will differ. If one group differs, there will be another group which also differs. So the alternative hypothesis would be that at least two of the groups differ. The other 8 groups may have the same value. Now total, therefore we calculate the total sum of square, which is sum of square of differences from grand mean for all the observations irrespective of groups. We also calculate between sum of squares. As the sum of squares of differences of group means from grand mean, each multiplied by number of observations in that group. Actually, the concept is very simple. Imagine that there is no within variation, then all the variation will be due to between. And that will happen if all the observations within a group have the same value as the mean of the group. So between sum of squares can be computed as imaginary by replacing all the observations by group means. And in practical terms, it is calculated as sum of squares of differences of group means from the grand mean, and each multiplied by number of observations in that group. Then within sum of square is the sum of squares of differences of all values from their group means of the respective group. And algebraically, it can be shown that total sum of square equal to between sum of square plus within sum of square. Since F distribution can be defined only in terms of degrees of freedom, so we have to say something about degrees of freedom also. For overall data, the degrees of freedom means degrees of freedom for total sum of square would be n minus 1, where n is the number of observations. You know, this is how you compute variance in sampling theory. Sum of square divided by degrees of freedom. So sum of squares of observations minus grand mean divided by number of observations minus 1. Now, between sum of square has k minus 1 degrees of freedom, where k is the number of groups and 1 is 1. So 1 less than the number of groups is the degrees of freedom for between sum of square. And within sum of square has the degrees of freedom for total sum of square minus for between sum of square. So n minus 1 minus k minus 1, which becomes n minus k. Between is k minus 1 and within is n minus k. And we get estimates of variance. One by dividing total sum of square by its degrees of freedom. Another by dividing between sum of square by its degrees of freedom, means k minus 1. And one by dividing within sum of square by its degrees of freedom, or n minus k. The expected value of the first and third is same as the variance of the population. It can be shown algebraically again that the expected value of the first total sum of square and means estimate of variance based on total sum of square. If you take expected value of that, that will be same as that of the variance of the population. And same thing can be said about within sum of square. So estimated value of estimate of variance of the population based on within sum of square is same as the true variance of the population. However, the expected value of the second, means between sum of square, is equal to or more than the variance of the population. It is equal only when the null hypothesis is true. If there are no group differences, then the three estimates of variances will be same. But otherwise, the expected value of the first and third will be same, and expected value of the second, means based on between sum of square, will be higher. Now, F ratio follows F distribution. So if the value of F is 1, then it means that there is no and F is defined as ratio of estimate of variance based on between sum of square to estimate of variance based on within sum of square. If the value of F is 1, then there is no significant difference between the groups. But how do we decide that if the value of F is this, suppose 2 or 3 or 4 or 4.2 or 7.2 or 8.9, then we will say that there is a significant difference. So as in case of other inferential statistics, we fix some probability P, say 0.05 or 5%, and calculate the value of F for those degrees of freedom for BSS and WSS. And if the calculated value of F is less than the tabulated value of F at P equal to 0.05, or maybe you prefer P equal to 0.01 or 0.001, then you say, then you take the decision that if calculated value is less than that, there is no significant difference, and if the calculated value is higher than the tabulated value, then the differences are statistically significant, and the null hypothesis is rejected. Now, there are some assumptions in application of ANOVA. All the K populations from which K samples are drawn have a common variance. Second, all the observations are independent of each other. That is, the method of teaching applied to one group has absolutely no effect on the observations in the other two groups. The model is linear. EIJ is a random error, showing a normal distribution with mean 0 and a fixed variance sigma square E. And the model Xij equal to mu j plus Eij. All group effects are estimated by using method of least square. And this is what we call ANOVA table. And your computer output will produce a table like this. Here, there are 3 rows: between groups, within groups, and total. Total, this sum of square refers to total sum of square. Degrees of freedom is 1 minus, total number of observations minus 1. In our example, total number of observations is 10 plus 10 plus 10, 30 minus 1, so 29. There are 3 groups, so degrees of freedom is for between groups would be 3 minus 1 or 2, and sum of square of between groups is 1103.267. The difference between sum of square for total and for between groups is 13542.200. This is sum of square for within groups. And degrees of freedom is again the difference between 29 and 2, which is 27, n minus k. Then we divide sum of square by degrees of freedom. This is mean square. The mean squares are estimates of variances of the population. I told you that if there are no differences between groups, then the two would be same, and they would be same as that estimated on the basis of total sum of square, means 14645.467 divided by 29. The values of mean squares for between and within will also be same. That, but here in this case, they are different, and ratio of mean squares means 551.633 divided by 501.563 is 1.1, and the f value for 5% level of significance is 7.68. Now, since 1.1 is less than 7.68, we will say that the null hypothesis is not rejected. In a modern way of interpreting findings of the ANOVA or inferential statistics in general, we also calculate sig. And while in the conservative model, we fix p-value and decide whether null hypothesis can be rejected or not rejected. Sig means that if we are going to reject the null hypothesis, what probability P would be probability of committing type 1 error, and that is 0.347. And in this case, what we do, if the value of the sig significance level is more than 0.05, then we accept the null hypothesis. If the value of sig was less than 0.05, suppose in place of 0.347, you have a value 0.0009, then you would reject the null hypothesis because that value is less than 0.05. Friends, no statistical technique can be applied indiscriminately. There are limitations of ANOVA. There may be 2 or more factors affecting the scores, while we are focusing only one. If we focus on one only, but there are 2 or more factors affecting the dependent variable, then we are not doing justice to the real structural model. The second, the teaching methods may actually differ, but since the composition of the subjects in different groups are not same, we do not find the difference. So we have to ensure that the subjects or individuals who participate in the experiment on different teaching methods are similar with respect to all those characteristics which might influence the final result. Likewise, we may find the difference, but it may not be due to teaching methods, but due to other reasons, as the composition of subjects is not same. Then there is heteroscedasticity. That is, the variances of the groups are not same. If a small differences between groups may not matter, but if there are significant differences, large differences between groups, then there is a problem of heteroscedasticity, and that makes the application of ANOVA limited. Then what are the options? learn from review of literature whether you need to use one-way ANOVA or two. If the causes or if the factors affecting the dependent variables are say two, then you have to go for two-way analysis of variance, because both the factors will have to be considered explicitly. If the total number of factors is three, then you have to go for three-way ANOVA. And it is always better to have large samples with randomization. And otherwise, in case of small samples, identify through review of literature what are the factors which might affect your dependent variable, and match your respondents or subjects with respect to all those characteristics. But ideally, for drawing causal inference, panel data on longitudinal study is always the best. Let me tell you that all major researches in the Western countries today are based on panel data, longitudinal study. Longitudinal study are believed to be the real studies to establish causality of any kind. Cross-sectional or survey-based or experimental researches have their limits. So that may also be kept in mind. Friends, sometimes you are applying ANOVA, but you are also interested in comparing means of two groups, or pairwise. You are interested in pairwise comparisons. You can go for conventional t-test, or you can go for t-test, which is part of ANOVA. T-test, which is part of ANOVA, if you want to compare two groups, and their means are mx1 and mx2, then the numerator part is same, mx1 minus mx2. In conventional T, your standard error would have been a square root of S1 square by N1 plus S2 square by N2. But here we take the mean sum of square for the error term, which is S, and in the bracket 1 upon N1 plus 1 upon N2 and square root of that, where S is the square root of the mean sum of square or the estimate of variance using the within sum of square. Degrees of freedom in this case would be N1 plus N2 minus 2. This test is more powerful in the sense that S is less than the S as square root of pooled variance in the earlier case. There may be a situation that the null hypothesis is not rejected using the conventional method, but is rejected using the ANOVA, because your denominator in this case would be smaller. As a matter of fact, if you go for two-way ANOVA, three-way ANOVA, four-way ANOVA, your sum of square, which can be attributed to error, will keep on decreasing, because you are taking into account, you are accounting for variation due to different factors explicitly. So the residual variance will decline and the value of S will decline. When the value of S, which appears in the denominator, declines, then the value of T will increase. So the chance of rejection of null hypothesis will be higher. And this is what we mean by saying that ANOVA provides a more powerful test even for making comparisons pairwise. In our example, we can compare two means with values 59.1 and 64.6 by using 501.563 as the value of S. Null hypothesis is still not rejected. Note that there are greater differences within the two groups than between the groups, and that is the reason why null hypothesis is not rejected. So here in ANOVA, always remember one thing, that although you are drawing inference about differences between groups, but you are able to do so only by comparing between differences within differences. So absolute differences between groups are not so important. Differences between groups in relation to within groups is the important or is the deciding factor on the basis of which you say that the differences are statistically significant or not. This is a general table of ANOVA and containing algebraic expressions for sum of squares, mean sum of squares, and F ratios. Sum of square total is sum of square within plus sum of square between. Sorry, sum of square total as given below the table is sum of square between plus sum of square within. This is what I told you earlier. Now, friends, you can show variations in the values of the dependent variable for different teaching methods, or as in this case, this is not the graph for the example which I gave you. This is a graph which I have taken from some other source. And the purpose is only to illustrate that for different groups, here blend 1, blend 2, blend 3, blend 4, variations of hardness in a different experiment are shown. And the variations, you notice two things. One, that blend 2 mean value is less than the mean value of hardness of blend 1. And in case of 3, it is higher than blend 2. In case of blend 4, it is higher than blend 3. But the relationship is not linear. So if you find significant differences between 4 blends, you are not in a position to say whether there is a linear relationship in blend level and the hardness. You can find difference. There will be significant differences, but differences does not mean that the mean values are falling or rising in the same direction. Now, this is also the problem in chi-square. You can only say that there are differences between different categories of attributes. Here also in ANOVA, you can only say that there are differences, but you cannot say whether differences are in increasing or decreasing order. Now, there is one very special aspect of errors in analysis of variance, and I want to draw your attention towards that. As done in some of the previous lectures, type 1 error is defined as probability of rejecting a null hypothesis even when it is true. Suppose a variable has 3 categories and you fix 0.05 as alpha for any one comparison. How many comparisons are possible? In case of 3 teaching methods, 3 comparisons are possible. Method 1 and method 2, method 1 and method 3, method 2 and method 3. Then the probability that there is no type 1 error in any of the comparisons would be 1 minus probability of committing type 1 error in any one comparison raised to power 3 or 0.857. Then the probability of committing type 1 error in the entire analysis would be 1 minus 0.857 or 0.143, which is not same as 0.05. For your analysis, then type 1 error is 0.143. So I wish to draw your attention toward this fact that although you are rejecting or not rejecting value of f, assuming p to be 0.05, in the entire analysis, your p value is 0.143, which is higher than 0.05. For type 1 error of 0.05, the overall alpha should be fixed at 0.016. If your alpha means type 1 error in any one comparison is 0.016, then only the type 1 error of the entire analysis will be 0.05. So for each comparison, when you are using t-test pairwise, then for each pair, you must fix type 1 error at 0.016. This is if you fix type 1 error of 0.016 for each pair, then for entire analysis, your type 1 error will be 0.05. Thanks. So friends, this is what analysis of variance means. Analysis to repeat, analysis of variance is used for comparing groups, and the basic idea is that in the data there are many types of variations. We divide in case of ANOVA, where there is one dependent variable and one independent variable. We estimate variance of the population by using three methods. One, sum of square for the total. Another, only by looking at the means of the groups. And third, by looking at variations within the groups. Ideally, if the null hypothesis is true, then the estimate should be same. And the estimate of mean sum of square or estimate of variance by using categories of the independent variables should be same as that obtained from within. But generally, this mean sum of square for between groups will be higher, and this can be shown algebraically than that of within. Now, so if you calculate F ratio or ratio of mean sum of square of between and mean sum of square of within, you will get a value more than 1. Either 1 or more than 1. If null hypothesis is correct and there are no within, then it will be 1, otherwise it will be more than 1. Now, using the statistical inferential theory, we have to find out what is that value of the ratio beyond which we will say that there is a significant difference. And this we say by using F distribution theory, because we know statistically that the ratio of variances follows an F distribution with certain degrees of freedom. The degrees of freedom of between would be number of categories minus 1, and within would be total number of observations minus number of categories. And by comparing calculated value of F ratio with that of the F distribution tabulated for appropriate degrees of freedom, we make a statement whether null hypothesis can be accepted, truly saying can be rejected or not rejected. Non-rejection is okay, but if null hypothesis is rejected, then we say that there is a significant difference between the groups. And at the end, I also mentioned that you can compare, you can make pairwise comparisons by taking two groups at a time. But remember that several such pairs may be possible, and in fixing the value of P for comparing two groups at a time, this P has to be different from 0.05 if in overall terms you want to attain a type 1 error of 0.05. And I have shown you with that, with an example, how that type 1 error should be addressed. So in a small presentation on ANOVA, these are the things which I wanted to say. Thank you.